This e-learning shows you important information on the commissioning of resistance thermometers. Resistance thermometers change their ohmic resistance when the temperature changes. Platinum is established as a resistance material in industrial measurement technology. The most common types are PT100 and PT1000, whose properties are defined in the standard DIN EN 6751. Among other data, this includes the characteristic curve and the tolerance classes of the sensors. A PT100 has a basic resistance of 100 ohm. The resistance change in the lower temperature range is 0.391 ohms per Kelvin and is nonlinear over the entire range. In the simplest case, a resistance thermometer can be connected via two wires. In the field device, here using the example of a JUMO D-Trans T06 transmitter, the sensor type must be selected accordingly. The linearization adapts the measured values to the corresponding sensor characteristics. If this is set to linear, the resistance value is displayed. With the selection PT100, the temperature assigned to the resistance value is displayed. The field device gives a low current into the measuring circuit and simultaneously measures the dropping voltage. The voltage drop of the supply lines is included in the measurement result. This means that the value displayed is too high. This can be compensated by entering the line resistance as an offset. However, the measurement in a two-wire connection is always subjected to the influences of ambient temperature and terminal resistances. As described, the total voltage at the sensor and the two supply wires is measured. With the three-wire connection, the voltage drop at one supply wire is measured by an additional wire. This measuring input is very high ohmic, so that practically no current is flowing. This means that no voltage drops across the third wire. The measurement includes only the voltage drop of the upper wire shown in the picture. This additional measurement result is multiplied by 2 and subtracted from the total voltage. Thus, the influence of the line resistances is compensated by the field device. The three-wire connection is the most common industrial measurement technology, but different terminal resistances can still affect the measurement results. The four-wire connection is also used to compensate different terminal resistances. Even the wire resistances can be different without affecting the measurement result. With a four-wire connection, the voltage drop is measured directly on the resistance thermometer via two additional measuring inputs. Due to the high impedance of these inputs, no voltage drops via these wires. Ready-built resistance thermometers can also be designed in 2, 3 or 4-wire technology. This refers to contacting right down to the sensor element. In the 2-wire version, the sensor connection cable in the protection tube results in higher resistance values and thus a higher temperature display. Depending on the material, cross-section and protection tube length, this has an influence of approximately 0.01 to 0.25 Kelvin. Looking at the tolerance classes according to DIN EN 6751, a resistance thermometer class A has a tolerance of plus minus 0.75 Kelvin at a temperature of 300 degrees Celsius. The offset of the sensor connection cable already corresponds to 1/3 of the total tolerance. The example illustrates why the standard requires for resistance thermometers with accuracy class better than class B a 3- or 4-wire design. As described before, a systematically higher temperature display results with a 2-wire connection, which can, however, be eliminated by a zero offset. The table shows the offset when using a PT100 per 1 meter supply line. If, for example, a copper wire with a cross-section of 0.34 square millimeter is used, this results in a 0.27 Kelvin higher temperature display per 1 meter of wire. Since the nominal resistance of the PT1000 is 10 times higher than that of the PT100, the influence of the supply line resistances is also reduced by the factor 10. If the accuracy requirements are not particularly high, the use of a PT1000 in a 2-wire circuit can be sufficient. If a 2-wire connection and a copper cable with a cross-section of 0.34 square millimeter is used, this results in an offset of only 0.027 Kelvin per 1 meter cable. All information about our seminars, webinars, e-learnings and reference books you will find at campus.jumo.net.